Hi, in this lecture we will see different types of spatial matrices. In the last lecture we have seen what matrix transpose is, and based on transpose we have seen two types of matrices, symmetric and skew-symmetric. Symmetric was A transpose is equal to A and skew-symmetric was A transpose is equal to minus A. Now similarly, like symmetric and skew-symmetric, we will see more types of matrices in this lecture, which have a well-defined meaning and their properties as well. So let's start. So first we have Singleton matrix. The simplest matrix, it is a matrix that has only a single element, which means how can you fit a single element? It means that you must have a single row and a single column. So a Singleton matrix will have one row, one column, and it will have only one element inside it, okay, and that is called a Singleton matrix. So a matrix that has only one element is called a Singleton matrix. So it will be of size 1 cross 1. So the number of rows will be 1 and number of columns will be 1, and every Singleton matrix will be a square matrix, right, because its number of rows and columns are equal. And it will be a diagonal matrix as well, because all the non-diagonal elements will be 0. There are no non-diagonal elements, there is only a single element and that lies on the diagonal. So it is a diagonal element matrix as well. It is a scalar matrix as well, and it might or might not be identity matrix. So the only Singleton matrix which is the identity matrix is this one. If you have a single element which is 1, then it is identity as well. But if the element is not 1, then it might not be identity as well. Like, so if the element is, let's say, 5, it is also a Singleton matrix, but it is not an identity matrix, because in identity matrix the element has to be 1, okay, the diagonal elements have to be 1. So these are some properties of Singleton matrix. It must have a single element, and this is how Singleton matrix looks like. Now asking you one question, is Singleton matrix, let's say, if you want to see, is the Singleton matrix always symmetric? Then a Singleton matrix is always symmetric, yes. Why? Because you have a single element, let's say K. If you have a single element K, what does symmetric matrix mean? A transpose must be equal to A. So if this is the matrix, then A transpose will also be K only. It will also have a single element, right? And hence it will be a symmetric. But now, is a Singleton matrix always skew-symmetric? No. It is not necessary that a Singleton matrix is always skew-symmetric. The reason is, in that case, diagonal elements must be 0. A transpose must be equal to minus A, and that can only happen if this element is 0. So the only Singleton matrix which is skew-symmetric is this matrix. This is skew-symmetric, but not in general, okay. So this matrix is 0 matrix as well, and it is skew-symmetric as well, but not, you cannot say that every Singleton matrix will be skew-symmetric. Same way you cannot say that every Singleton matrix is identity as well. But square, diagonal, scalar and symmetric, these properties will work for Singleton matrices as well. Cool. Now let's look at the next type of matrix. Next we have idempotent matrix. Idempotent matrix. So what is the idempotent matrix? It is a square matrix. Just like symmetric, skew-symmetric, this also must be a square matrix that when multiplied with itself results in the original matrix. So the property is A square must be equal to A. Now notice that you can only compute A square for A square is what? It is A into A. And we can only compute A square for square matrices only, because if A is of dimension m cross n and you are multiplying it with m cross n, n and m must be equal, and hence A square can only be computed for square matrices, and hence for this property to work, A must be a square matrix. So every idempotent matrix will be a square matrix as well. So it is a square matrix that when multiplied with itself results in the original matrix, which means A square must be equal to A. Okay. Okay, let's see an example of idempotent matrix. So there are 3 examples given. We just have to check these matrices are idempotent or not. So first is A is this matrix. So let's calculate A square here. A square will be 4, 12, minus 1, minus 3 times 4, 12, minus 1, minus 3. So if we do the multiplication, we will have 4 4s are 16, minus 12 is 4. Then 4 minus 4 plus 3 will be minus 1. Then we will have 48 minus 36 will be 12, and then we will have minus 12 plus 9, which is minus 3. So essentially we got A back. We got A back. We just calculated A square and we just got the matrix A back, and hence A is idempotent. Matrix A is idempotent. Okay. And in matrix B, here we can see we have 4 elements, 1 0 0 0. It's also a 2 cross 2 matrix. So if we calculate B square, it will be 1 0 0 0 times 1 0 0 0, and the matrix will be 1 plus 0 is 1, then 0 plus 0 is 0, then 0 plus 0 is 0, then 0 plus 0 is 0. So we again got the matrix B back. So B square is also equal to B. You can see here B square is also equal to B, and hence matrix B is also idempotent. Matrix B is also idempotent. A is idempotent, B is also idempotent. If you look at matrix C, so C square will be equal to 0 1 1 0 times 0 1 1 0. So it will be 0 plus 1 1, then 0 plus 0 0, then we will have 0 plus 0 0, and then we will have 1 plus 0 1. So we got I. We got the identity matrix here. We didn't got C. We didn't get C back. This is not equal to C, right? This is not C. This is I actually. So C square is not equal to C, and hence C is not idempotent. C is not idempotent. Matrices A and B are idempotent, but matrix C is not idempotent. Okay. So this is how you check idempotency. If A square is equal to A, then A is idempotent, and A must be a square matrix. Okay, then only this will work. Cool. Now moving on, these are some of the properties of idempotent matrices. First is identity matrices are idempotent. Every identity matrix will be idempotent. Why? Because I square will be what? It will be I into I, and I into I is always I. For any identity matrix, the square of it is always identity. Even like you can write it this way: identity matrix to the raise any power, you will get the same matrix back. Okay, we have already seen this property. If you want, you can take an example. Let's say size 2 identity matrix. If you multiply it with itself, you will get the same matrix back. And if you keep on multiplying I to it, you can keep on multiplying the identity matrix to it. You will keep on getting the same matrix back. Okay, and so on. You can keep on doing it. And hence for any identity matrix, its a square will be equal to itself, and hence it is idempotent. Okay, every square matrix will be idempotent. Now next is zero matrices are also idempotent. Very obviously, like if all the elements are 0, let's say we take a 2 cross 2 matrix, then even if you take the square of it, all the elements will remain 0. Even if you take cube, even like you can write the same property, 0 matrix to the power any value, you will get the 0 matrix back. And hence 0 matrices are also idempotent. Okay, 0 matrices are also idempotent because z square will be equal to z only. Now if a matrix A is idempotent, then A to the power n is also idempotent for all natural numbers n. For any natural number n, if A is idempotent, then A to the power n will also be idempotent. Okay, this is a very important fact. So let's try to prove it. The property is if A is idempotent, then A to the power n is also idempotent. For n greater than equal to 1. Okay, for n is a natural number. You can write it this way. Okay, n is a natural number because for negative n, it will be A inverse, A to the power minus 2, that they are different matrices. Inverse we will say later. Okay, we are not discussing inverse right now. So we are not discussing negative powers. Okay. So if A is idempotent, then A to the power n is also idempotent. Like how do we check this? How do we prove this? Very simple. If A is idempotent, then A is a square matrix. Let's say A is of size n cross n. Okay, and it is idempotent. It means that A square will be equal to A. Now if you check A to the power n, we will just have to check its square. A to the power n square will be what? A to the power n square will be A to the power n into A to the power n. Okay. So essentially it is A to the power 2n. It is essentially A to the power 2n. And now you can write it like, so since every a square is equal to a, every a square is equal to a, every two a's will become a single a. Think of it this way, right? Every two a will become a single a. And hence what will happen essentially, so here it is like 2n. So if you take like any value of n, let's say n is equal to 4, it is like a to the power 8. So you will have 8 a's, that will become 4 a's, that will become 2 a's, and that will become 1 a, and so on. Okay, so how do we prove it? Let's say like you can, if you can take any value of a essentially, and it will just boil down to a single a. The reason is, so you can keep on writing. So yeah, let me do it differently. So if a square is equal to a, if a square is equal to a, then a cube will be what? It will be a square into a, which is a into a, which is again a square, which is a. So if a square is a, then a cube will also be a. So for every idempotent matrix, actually every power will be same matrix only. For every, this is a new property, for every idempotent matrix, because a square is a, and hence a cube must also be a only, and hence a to the power 4 will also be a only, because it is a square into a square, which is again a, and hence like every power of a will be equal to a only for any idempotent matrix, and hence a to the power 2n will also be equal to a only, and a to the power n square will be a, and hence a to the power n is also idempotent, which means you can write that any power of a is actually a only. That's the same thing, actually writing the same thing. So if a is idempotent, a to the power n is also idempotent, which means a to the power n square is also equal to a. Okay, so this is this property. And next is, if a is idempotent, then I minus a is also idempotent. If a is idempotent, then I minus a is also idempotent. Let's try to prove this one as well. So the property is, if a is idempotent, then I minus a is also idempotent. Okay, so let's try to see it. So if a is idempotent, again a square is equal to a. So I minus a, what will happen to I minus a? I minus a square will be I square minus 2ia. Okay, you cannot, like, it will be essentially I minus a times I minus a. Okay, so it will be I into I, which is I into I is I only, right? Minus I into a minus a into I plus a square. So I is I only, and IA will be a only, and AI will be a only. If you multiply any matrix with identity matrix, you will get the same matrix back, and plus a square. A square is a, because a is idempotent, and hence a square is a. Now minus a and plus a will cancel, and you will get I minus a again. So we just proved that I minus a whole square is nothing but I minus a. Okay, which means a square is equal to a. Whenever, like, if you take I minus a as q, we just proved that q square is equal to q, which means q is idempotent, which means I minus a is also idempotent. We just proved that I minus a is also idempotent. If you want, you can take an example to see this as well. In the last slide we saw some examples. Let's take this one. Let's take an easier one. 1 0 0 0. This is idempotent, right? 1 0 0 0. So let's take this example. Okay, so we have just seen that 1 0 0 0 is idempotent. Let's say a is this. So I minus a will be what? It will be 1 0 0 1 minus a. A is what? 1 0 0 0. So you'll get the matrix 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 0 is 0, and 1 minus 0 is 1. So this is the matrix you will get. Now if you take the square of this, I minus a square will be 0 0 0 1 times 0 0 0 1. So you'll get 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, and 0 plus 1 is 1. So you got the same matrix back. You got the I minus a, this matrix back, and hence I minus a is also idempotent. This matrix is also idempotent. Okay, its square is equal to the same matrix. And hence the property holds, the property that we saw about idempotent matrices, these all properties hold true for idempotent matrices. Okay. So now let's look at the next type of matrix. It is the involutory matrix. So what is an involutory matrix? Again, it is a square matrix. Just like idempotent, this is also a square matrix. When multiplied by itself results in an identity matrix. So in idempotent, they were like don't get confused with the terms. Idempotent means a square is equal to a, and involutory means a square is equal to I. Okay, which means the square of the matrix must be equal to the identity matrix. Later when we see inverses, we will see that it also means that a should be equal to a inverse. Okay, but that part we will see in inverses. Okay. So what is an involutory matrix? It is a matrix which if you square it, you will get the identity matrix. Okay, it can be of any size, but again it should be a square matrix of any size, n cross n matrix. Okay. So again let's see some examples and see if the matrix is involutory or not. So we have the first example, 2 1 minus 3 minus 2. It is a 2 cross 2 matrix. It is a square matrix. Now let us check a square. A square is 2 minus 3 1 minus 2. Then 2 minus 3, 1 and minus 2. So if you multiply these two matrices, you will get 4 minus 3 is 1, then 2 minus 2 is 0, then minus 6 plus 6 is 0, then minus 3 plus 4 is 1. So which is the identity matrix? It is the identity matrix. Okay, this is the identity matrix of size 2 cross 2. So I took the square of A and I got the identity matrix. Now if I take A cube, which means a square into a, which means I into a will again become a, and if I take a to the power 4, it will be a square into a square, which is I into I, which is again I, and so on. So I will keep on getting a, then I, then a, then I, then a, then I, and so on. So if the matrix is an involutory matrix, then like if you have a square, a cube, a to the power 4, a to the power 5 and so on, these will be a, then I, then a, then I, then a. For odd powers it will be a, for even powers it will be I, like that. And if the matrix is idempotent, in idempotent matrix all the powers are equal to a only. So for an idempotent matrix, a and a square and a cube and a to the power 4 and so on, all of them will be equal to a only. This is something that we have already seen. Okay, so these are some properties of involutory matrix and idempotent matrices. Now let us look at matrix B. So matrix B square is 1 0 0 0 times 1 0 0 0. So it is 1, then we will have 0, then we will have 0, and then we will have 0. So B square is equal to B. B square is not equal to I here. Okay, this is not the identity matrix, and actually B is a idempotent matrix, but not an involutory matrix. Okay, because for B to be an involutory matrix, B square must be equal to I, and since B square is not equal to I, B is not involutory. So A was involutory, but B is not. Okay, now let us look at C. What is C square? C square will be 0 1 1 0 times 0 1 1 0. So if you do this multiplication, 0 plus 1 becomes 1, then 0 plus 0 becomes 0, then 0 plus 0 becomes 0, and then 1 plus 0 becomes 1, which is equal to I. So C square is equal to I, and hence C is involutory. So here in this case, A and C are involutory and B is not involutory, because we just took a square and checked we get identity matrix or not. Cool. Now let us look at some properties of involutory matrix. Last one we have already seen. If a matrix A is involutory, then A to the power n is I if n is even, and A to the power n is A if n is odd. We have already seen that, right? Because for all the even powers we are getting I, and for all the odd powers we will get A. We have already seen the proof. It's very simple, right? You can keep on multiplying A and you will get that. Cool. So this is something that we have already seen. Now identity matrices are involutory. Very simple to prove. So identity matrix, if you take the square of it, you will get I into I, and I into I is I only. So identity matrix square is equal to I, which is the condition for involutory matrix. What is involutory matrix? Its square is equal to identity matrix, and identity matrix square is identity matrix, and hence identity matrices are involutory. And we have already seen that identity matrices are also idempotent as well. So identity matrices are idempotent and involutory both. Okay. So this is the property. Cool. Next, if a matrix A is involutory, then a to the power n is also involutory for all natural numbers n. Same property we have seen for idempotent as well. Now we can prove this one also. So if A is involutory, what will it mean? A to the A square will be I, right? And what will be a to the power n square? So it will be a to the power 2n. Okay. So here you can see 2n. 2n will be what? 2n is an even number. 2n is an even number. 2n is an even number, and we have already seen that if you raise an even number to the power of a, if a is involutory, and if you are raising a to an even number, to an even power, you will get I. You will get I, right? If you raise a to an even power, then you will get I, and hence a to the power 2n will be equal to I, and hence a to the power n square is I, which means a to the power n is involutory as well, which means a to the power n is involutory, and hence proved. If a is involutory, a square is I, and if a is involutory, a to the raised any even power will be I, and a to the power n square and hence becomes I, and hence a to the power n is also involutory, which means if a is involutory, a square, a square, a cube, a to the power 4, a to the power 5, all these matrices are involutory in nature. Okay, and same thing was true for idempotency as well. Cool. So these are a few properties of involutory matrix. Okay, next up we have nilpotent matrix. So what is a nilpotent matrix? It is a square matrix that when raised to a certain positive integer power results in the zero matrix. Okay, so a to the power k will become 0 at certain point. We don't know where, but at certain point in time a to the power k will become 0. And if you observe the fact that if a to the power k becomes 0, which means 0 means here 0 matrix, not the integer 0, right? Because if you are raising a matrix to certain power, it will become a matrix only. So here 0 is the 0 matrix. Okay, here 0 is the 0 matrix. So if you raise the matrix A to certain power, you will get the 0 matrix. Now if A is n cross n, obviously this is also an n cross n 0 matrix. Cool. Now the point is, even now after this it will remain 0. So if you calculate now, if a to the power k plus 1 also, it will just become a to the power k into a, which is 0 into a, which will be 0. You multiply any matrix by 0 matrix, you will keep on getting 0 matrix. So after power k, you will keep on getting the 0 matrix, but before power k you can get any matrix. Okay, that is like we don't care about that. But at certain power, like what will happen, like let's say you have a matrix A, then you calculated a square, that is some matrix, then you calculated a cube, that is some matrix, and so on. Let us say at a to the power 7 you got the 0 matrix. After that you will keep on getting 0 matrices. Okay, like that. And if this happens at certain point in time, then A is called nilpotent, which means it has nil potential. It has the potential to become nil at certain point in time if you keep on raising the power. Okay, so a square matrix that when raised to a certain positive integer power results in the 0 matrix, and k is called, so this particular number k here in this case, let's say a to the power 7 was the first power where it became 0. Before that it was not 0. So that first power is called nilpotency or the index of the matrix. Okay, it is called the nilpotency of the matrix. That k, the smallest value of k, is called the nilpotency of the matrix. Okay, so let's see an example. Here we have a matrix A. Let us try to calculate a square. Okay, 1, 2, minus 1, then minus 3, 0 and 3, then 1, 2, minus 1. Okay, and we will have to multiply this matrix with itself. So 1, minus 3, 1, 2, 0, 2, then minus 3, 1, minus 1. Okay, so if you calculate the product, what will you get? It will be 1 minus 6, 1 minus 6, then plus 1, right? 1 minus 6 and minus 1, sorry. So it will be minus 5, minus 1, minus 6. Okay, then the second number will be minus 3 plus 0 plus 3, which is 0. Okay, then the third number will be 1 minus 6 minus 1. Okay, 1 minus 6 minus 1. Okay, it's the same thing. Okay, so it will become minus 6 again. Cool. Then you calculate this number, it will become 2 and then 0 and then minus 2, it is 0. Okay, then you will calculate the middle number, it will be minus 6 plus 0 plus 6, so it is 0 again. Okay, now if you calculate the 2 comma 3 number, it will become 2 minus 2, it is 0. Then you will have like minus 1 plus 6, minus 1 plus 6 and then plus 1, so it is plus 6. Here at this position we will have plus 6. Then we will have plus 3, 0 minus 3, so this will become 0. And then here we will have minus 1 plus 6 plus 1, again we will have plus 6. So this is what we will have. If you calculate a square, the matrix is this. Still we don't have the 0 matrix. A square is a matrix like that. Now if you calculate a cube, now if I calculate a cube will be what? It will be a square into a. You can multiply it on the right or left, it doesn't matter, you will get the same matrix, right? We already know this property. So a square is what? Minus 6, 0, 6, 0, 0, 0 and then minus 6, 0, 6. Okay, this is 0. And you have to multiply it with a. A is what? 1 minus 3, 1, then 2, 0, 2, then minus 1, 3, minus 1. So if you multiply these two matrices, what will we get? We will get minus 6 plus 6, which is 0. Then we will have my 18 and minus 18, so 0. Then we will have minus 6 plus 6, so again 0. And then we will have 0, 0, 0, so 0. So actually this row is entirely 0, so you will get zeros only in this row. Okay. Then you will have 6 minus 6, which is 0. Then you will have minus 18 plus 18, which is 0. And then you will have 6 minus 6, which is 0. So we got the 0 matrix. We got the 0 matrix. 3 cross 3 0 matrix. Right? And we just found out a cube is 0. And hence we found a number. We actually were able to find a number which makes a to the power k 0, which means A is a nilpotent matrix. It is a nilpotent matrix and its nilpotency or the index of this matrix is 3. The smallest number which makes power as 0 is the number 3 and hence the nilpotency of this matrix is 3. Okay. So this is what nilpotent matrices are. Cool. Next, similarly we have periodic matrices as well. So periodic matrices are what? After a certain point in time their powers repeat. So what will happen here? Let's say we have A, then if we calculate A square, it is a different matrix. Let's say after then we calculated A cube, that is a different matrix. Generally period is a concept that applies in various algebra. In matrix algebra it applies like this, which means periodicity means after a certain point things start repeating. So what will happen? A square, A cube, A to the power 4, let's say and then A to the power 5 again became A. Let's say again A to the power 5 became A. But these matrices are different. Okay. So if A to the power 5 became A to the power 6 will be what? It will be A to the power 6 will be A to the power 5 into A, which is A to the power 5 is A into A, which is A square. So A to the power 6 again will become A square, right? And hence A to the power 7 will become A cube, because A to the power 7 is A to the power 6 into A, which is A square into A, which is A cube. Similarly, A to the power 8 will become A to the power 4. And then again A to the power 9 will become A. A to the power 9 will again become A, because A to the power 9 is what? A to the power 9 is A to the power 8 into A, which is A to the power 4 into A. Okay. We should not have done it this way. Actually, we can write it this way. A to the power 9 is actually a to the power 5 into a to the power 4, which is a into a to the power 4, which is a to the power 5, which is a. Right? Yeah, you can do it anyway. But again, yeah, like in periodicity, what will happen? The powers will repeat, and 8 ke baad like 9 will be here, and then a to the power 10 will be equal to a square. Then a to the power 11 will be here, and then a to the power 12 will be here, and so on. So in every periodic matrix, this will happen. At a certain point in time, the powers will start repeating. Here I assume that the period is 4, but you can have different periods. But the idea is that after a certain point in time, the powers will repeat, and then you will have the same powers. Which means at a particular point in time, a to the power k becomes a. See, in nilpotent matrix, at certain point in time, a to the power k becomes 0, which is the 0 matrix. But in periodic matrix, at a certain point in time, a to the power k becomes a. We don't call it k, we call it k plus 1. We call it k plus 1. Why? Because we are calling it k plus 1 because we want to call k as the period of the matrix. Here the period is 4 because we have 4 different powers of a. Here we have 4 different powers of k, and hence the period of this particular matrix is 4. And if you observe that, the first time the power repeats is k plus 1. And hence we are saying that a matrix is periodic if it is a square. Firstly, it should be a square matrix, and when it raised to a certain positive integer power, results in the same matrix, which means a to the power k plus 1 becomes a. The power at which it becomes a is called k plus 1. So here in this case, k plus 1 was equal to 5, and hence k is equal to 4. Okay, and this value of k is called the period of the matrix, because this is what like different powers of a we have in the matrix. Okay, so for some positive integer k, if a to the power k plus 1 is equal to a, then a is called a periodic matrix, and k is called the period of the matrix. K is called the period of the matrix. Okay, cool. Let's see an example. With an example, it will become more clear. So this is the matrix that we have: 1 minus 2 minus 6 minus 3 2 9 2 0 minus 3. Okay, so in this matrix, let's try to calculate a square. A square will be 1 minus 2 minus 6, then minus 3 2 9, then 2 0 minus 3. We will multiply this matrix with itself: 1 minus 2 minus 6, and then 2 0 minus 3. So what will we get? We will have 1 plus 6 minus 12. So 7 minus 12 is minus 5. Okay, then the second element will be minus 2, minus 4, and 0. So minus 6. Then the third element will become minus 6 plus minus 6 minus 18, then plus 18. So it is minus 6. Then this element will become minus 3 minus 6, and then plus 18, which is plus 9. Then this element will become 6 plus 4 plus 0, which is 10. Then we will have 18 plus 18 minus 27, which is 9. Which is 9. Okay, and then we will have this element as 2 plus 0 and minus 6, which is minus 4. Then we will have minus 4 plus 0, which is minus 4. Then we will have minus 12 plus 0 plus 9. Minus 12 plus 0 plus 9, which is minus 3. Okay, so this is the matrix that we got. This is what a square is. Now let's try to compute a cube in the same fashion. If you compute a cube will be minus 5 minus 6 minus 6 then 9, 10, 9, then minus 4, minus 4, minus 3 times a, which is 1, minus 2, minus 6, then minus 3, 2 and 9, then 2, 0, minus 3. Okay, if we compute this matrix, what will we get? We will have minus 5 plus 18 and then minus 12, which is 6 minus 5, which is 1. Okay, we will get 1 here. Then we will have minus 10, 10 minus 12, 10 minus 12 and then 0, so minus 2, so we'll get minus 2 here. Then we will get 6 5s are 30, minus 9 6s are 54 and then plus 18. Okay, so this is 48 minus 54, minus 6. Okay, minus 6 is what we will get here, and I am starting to get a feeling we will get a back. We will get a back. Okay, let's finish it anyway. So we will have 9 minus 30, 9 minus 30 plus 18, which is 27 minus 30, which is minus 3. So we'll get minus 3 here. Then we will have minus 18 plus 20 and then 0, which is plus 2. Then we will get minus 54 plus 90 and then minus 27, which means minus 81 plus 90, which is plus 9. Okay, we will get plus 9 here. Then we will have minus 4 plus 12 minus 6, which is 6 minus 4 is 2, so we'll get 2 here. Then we will have minus 4, which is 8 minus 8 plus and 0, which is 0, so we'll get 0 here. And then we will have last element as 24 minus 36 plus 9, which is 33 minus 36 minus 3. Okay, minus 3 is what we will get here. So this is what we get. So essentially we get a back. Essentially we got a back. Okay, so what happened? We got a, then a square was a different matrix, then a cube was again a. And you can check that now a to the power 4 will again be a square, then a to the power 5 will again be a, then a to the power 6 will again be a square, and so on. And the first power which became equal to a was a cube, was the first power which became equal to a. It was the first power. And this 3 is equal to k plus 1. We call it k plus 1. And hence k is equal to 2, which means the period of this matrix is 2. It is a periodic matrix with period 2, because we only have 2 different powers of a available, a and a square. And all other powers are just repetition of these 2. Okay, this is what is a periodic matrix. Okay, next look at triangular matrices. So there are 2 types of triangular matrices possible. One is lower triangular matrix and other is upper triangular matrix. And very simple architecture they have. Like firstly, this concept only applies on square matrices, okay, which have a diagonal, okay, which have a primary diagonal. So if this is a square matrix, this is the diagonal, and if all these elements are 0 and only these elements have some information, this is upper triangular matrix. This is upper triangular, okay, because only upper triangle contains some information. This is an upper triangular matrix, okay. And similarly, if you have another square matrix and this is the primary diagonal, and if all these entries are 0 and only this particular part contains some information, then this is called a lower triangular matrix, because only the lower triangle contains some information and all other elements are 0. Okay, so this is how we define upper triangular and lower triangular matrix. Now a very important point here to notice, like if I take any square matrix, let's say 4 cross 4, if A is a square matrix of size 4 cross 4, A11, A12, A13, A14, then A21, A22, A23, A24, then A31, 32, 33, and then 34, 41, 42, 43 and 44. This is a 4 cross 4 square matrix, right? So here in this matrix, what happens is all the diagonal elements, how are they denoted? We have already seen this. So all the diagonal elements are represented by AII, which means their row number and column number are same. Or you can also write it this way, that they are essentially Aij such that I is equal to j. Now if you look at all the elements above the primary diagonal, which means these elements, these are the elements which are above the primary diagonal, right? So they have an interesting property. They have their j greater than I. For all of them, j is greater than I. Note this point, right? Their j is greater than I, which means their column number is greater than their row number for all these elements. And similarly, for all the elements which are in the lower part of the diagonal, which are lower to the diagonal, they have their row number greater than the column number, right? Their I value is greater than their j value. So for all the elements in the lower, at the lower part of the diagonal, we will have I greater than j, which means row number is greater than the column number. Here I is 2 and j is 1, I is 3 and j is 2, and so on. So for all these matrices, all these elements, I is greater than j, and for all these elements, I is less than j. Okay, so what will happen now? We don't care about diagonal. Diagonal elements can be anything, but in an upper triangular matrix, all these elements where I is greater than j, these will be 0. All these elements will be 0, and all the information will be present either in the diagonal or above it. Essentially, all these elements must be 0. If I is greater than j, then the element must be 0, and this is the condition for upper triangular matrix. And for lower triangular matrix, all these elements must be 0, which means if I is less than j, then the element must be 0, and it is the condition in lower triangular matrix. So in a lower triangular matrix, all the information will be present either in the diagonal or on the lower half. Okay, so this is what happens. Now let's see the formal definition. So the formal definition says that in a lower triangular matrix, all the entries above the main diagonal, which means I is less than j. So all the entries above the main diagonal are 0, which means for a lower triangular matrix generally denoted by L, if the ijth element is Lij, then Lij will be 0 for all I less than j. So if I is less than j, which means this condition, all these elements are 0. And similarly, in an upper triangular matrix, all the elements below the main diagonal are 0, which means it is generally denoted by U, okay? And the ijth element is Uij, then Uij will be 0 if I is greater than j, which means if I is greater than j, which means all the lower elements, these must be 0 in an upper triangular matrix. Cool. So this is how lower triangular and upper triangular matrices are defined. Now let's see some examples. So here we have a few examples. So we just have to tell what type of matrices these are. So they are all square matrices firstly. So we can define lower and upper triangular matrix. Now here, if you see, all the information is present in the lower triangle, and all the elements above the diagonal, are 0, and hence this is a lower triangular matrix. Right? And if you look at this particular one, here all the information is present in lower, you can say that all the information is present in the lower triangle, and you can also say that all the information is present in the upper triangle. Actually, it is both lower triangular and upper triangular. Because all the elements above the primary diagonal are also 0, and all the elements below the primary diagonal are also 0. So this is both. It is both lower triangular and upper triangular. Actually, all the diagonal matrices are both lower and upper triangular, because only information resides in the diagonal. So you can always say that all the information above and below are 0. So all the diagonal matrices will be both lower and upper triangular. Then we have this one. So here all the elements below the diagonal are 0, and hence all the information is lying on the upper triangle, and hence it is an upper triangular matrix. This one is an upper triangular matrix. Okay, so these are a few examples. Always note that in a lower triangular matrix, all the elements in the upper triangle are 0, which means all the elements a, I, j will be 0 if I is less than j, which means column number is higher than the row number. For this element was a12. Here the column number was greater than the row number. This was the only element with this property. And in an upper triangular matrix, let's say C, this is a C, so Cij must be 0 if I is greater than j, which means row number is greater than that column number. So for all these elements, here this was the element C21, this was the element C31, this was the element C32. So for all these three elements, I was greater than j and they all were 0. So this is the criteria and this criteria is satisfying, and here both are 0 actually. Cool. Now let us look at a few properties of triangular matrices, which means some properties of lower triangular and upper triangular matrices. So both of them are closed under addition, which means sum of two upper triangular matrix will be an upper triangular matrix and sum of two lower triangular matrix will be a lower triangular matrix. Very simple to see, because if you add an upper triangular matrix, it will have all the information here and all these elements will be 0. And if you are adding it with another upper triangular matrix, firstly addition will only be possible if the sides are same. Firstly, if this is n cross n, this also must be n cross n, otherwise addition is not possible. So here also all these elements will be 0 and you will have few elements here. If you add them, addition happens element by element. So 0 will be added to 0, so these elements will still remain 0, right? And all the information will be present here only. So the final matrix will also be upper triangular, and same will happen for lower triangular matrix as well. So it is very easy to see. If you want a formal proof, you can say that if you are adding matrix A with matrix B, and if ijth term in A is Aij and ijth term in B is Bij, then we know that in the sum, let's say C, the ijth term will be Cij and Cij will be Aij plus Bij, because this is how addition happens, right? And for a upper triangular matrix, what happens if I is greater than j? If I is greater than j, this element is 0, and if I is greater than j, this element is also 0, and hence 0 plus 0 will be 0 if I is greater than j, right? So Cij, for Cij also this will happen, and hence this is the formal proof. You can prove it this way. Cool. Now same thing happens for subtraction as well. Even if you subtract matrices, 0 minus 0 will be 0. So you can add a minus here, and even if you add a minus here, 0 minus 0, this entire part will remain 0 only, and hence the subtraction of two upper triangular matrices will be an upper triangular matrix, and the subtraction of two lower triangular matrices will be a lower triangular matrix. We don't need to prove it. Okay, you can do it as a homework. Cool. Now let's look at the next property. Next we have closed under multiplication. This is very important. So product of two upper triangular matrices is an upper triangular matrix, and the product of two lower triangular matrices is also a lower triangular matrix. So they are closed under multiplication as well. So the property that we are discussing is if A n cross n is if A and B is also n cross n, then only multiplication is possible, right? So if A and B are upper triangular, then AB will also be an n cross n matrix. The multiplication is also upper triangular. Then AB is also upper triangular. This is the property that we are looking at. So how do we prove it? So if A is upper triangular, then we can say that Aij will be 0 if for upper triangular matrix, lower triangle will be 0, which means if I is greater than j, then the element will be 0. And if B is upper triangular, we can also say that Bij is also 0 if I is greater than j. Okay. So now what will happen for C? Any general element in C, so let me call it jk instead, because we want to do multiplication. So we will say that Bjk will be 0 if j is greater than k, because for multiplication the notation it will become easier for me. So in multiplication, let's say AB is equal to C. Let us say that the matrix multiplication of matrices A and B is the matrix C. Then the ijth element of C will look like, so ikth element of C will look like summation j is equal to 1 to n. We will take the ith row of A and kth column of B. Ith row of A, which means Aij, times kth column of B, which means Bjk. So k will remain fixed here and I will remain fixed here, and j will go from 1 till n. This will happen. Okay, so this is the value of Cik. Summation j equal to 1 to n Aij times Bjk. Now what will happen? So I can, we know that Aij is 0 if I is greater than j, but here j can be greater than I, or like both can happen. So I can break it down into two terms. So let's break it out into j is equal to 1 to, because if I is greater than j, then Aij is equal to 0. So let's break it down into j is equal to 1 to I minus 1 Aij times Bjk, and plus summation j is equal to I to n Aij times Bjk. Now when j is equal to I to I minus 1, so I just broke down j into like 1 to I minus 1 and I to n. Okay, I just broke it into two terms because j is going from 1 to n and I just broke it at I. Okay, so the point is, in this entire sum, j will go from 1, 2, 3 up till I minus 1. So for all these values, j will be less than I. J will be strictly less than I, right? And if j is less than I, Aij is 0, which means in all these terms, in all these terms, Aij will be 0 because I will be greater than j. So think about it. It will go from AI1, AI2, AI3 and AI minus 1. Essentially, j will be less than I. And if j is less than I, Aij is 0, which means this entire term will become 0. Now, if we look at this term, here what is happening? Here j is greater than I. Here j is either greater than or equal to I. In all these terms, here j is greater than or equal to I. But if you look at this particular term, we already know that we want to make comment for Cik only if I is greater than k. I just want to make comment for I greater than k because I want to prove that the matrix C is an upper triangular matrix, right? I want to prove that the matrix C is an upper triangular matrix because I considered A and B as upper triangular. To prove that C is upper triangular, I just need to consider the values where I is greater than k, because if I prove that for I greater than k, Cik is 0, it means that all the lower triangular matrices values are 0, which means the matrix is upper triangular, right? So I just need to consider I greater than k case. And there I need to prove the elements are 0. I don't care if I is less than or equal to k, any element can be there, right? So if I is greater than k, j must also be greater than k in this particular setup. In this particular setup, since j is greater than or equal to I, and we are only talking about the case where I is greater than k, it means that j is also greater than k. And if j is greater than k, we know that Bjk is 0. So either this term will be 0 or this term will be 0. In this particular sum, Aij will be 0, and in this particular sum, Bjk will be 0, and hence this term will also be 0. They both are zeros. So 0 plus 0 will be 0. So we just proved that Cik will be 0 if I is greater than k, which means that the matrix C is upper triangular. Therefore, the matrix C is upper triangular. And same proof can be done for lower triangular as well. There you will just have like opposite things, right? I less than j, j less than k, and sum will be slightly different. You can try it on your own. The same proof can be done for lower triangular as well. If A and B are lower triangular, then AB is also lower triangular. You can do it on your own, okay? We can take an example for this one as well. Let's take A as a lower triangular. Let's take two lower triangular matrices, okay? So let's say A is 1, 0, minus 1, 2, 3, 1, and then 0, 0, 0. This is a lower triangular matrix, right? And matrix B is 1, 1, 1, 0, 0, 0, 2, 0, minus 1. So A and B both are lower triangular matrices, and they are both 3 cross 3 matrices. They are both lower triangular, right? So if I calculate the product AB, it will become 1, 0, 0, 2, 0, 0, 3 1 minus 1 times 1 0 0 2 1 0 and 0 minus 1 1. So if you multiply these two matrices, what will we get? We will get 1 into 1 plus 0 which is 1. Then we will have 0 plus 0 plus 0 which is 0. Then we will have 0 plus 0 plus 0 which is 0. And then here we will have 2 plus 0 plus 0 which is 2. Then we will have 0 plus 0. Okay, 0 plus 0 plus 0 which is 0. Then we will have 0 plus 0 plus 0 again 0. Then we have 3 ones are 3 plus 2 5 plus 0 5. And then we will have 0 plus 1 plus 1, 0 plus 1 plus 1 which is 2. And we will have 0 plus 0 minus 1 which is minus 1. So this is the matrix that we will get, and here also you can see it is lower triangular. So if A and B are lower triangular, AB is also lower triangular. So this is what we have seen in an example as well here. Cool. Okay. So let me write it here. This is also lower triangular. Cool. So this is the property that we saw, product of two upper triangular matrices and product of two lower triangular matrices. Next is closure under scalar multiplication. This is very simple. If you multiply an upper triangular matrix by a scalar, you will get an upper triangular matrix, and if you multiply a lower triangular matrix by a scalar, you will get a lower triangular matrix. It is very easy to prove because every element gets multiplied by k, and all the elements which are 0, they will be multiplied by k and they will remain 0 only, and hence lower triangular matrix will remain lower triangular. So think about it. In an upper triangular matrix, if I is greater than j, aij is 0. And if you multiply the entire matrix by k, what will happen? Even then, if I is greater than j, k times aij will also be 0. And hence k times a is also upper triangular. And same for lower triangular. Okay, so this is a very simple proof. You can do it on your own. If the matrix is upper triangular, then the scalar multiplication will be upper triangular. And if the matrix is lower triangular, then its scalar multiplication will be lower triangular. Okay, cool. Now let's move to the next property. Next we have the transpose of an upper triangular matrix is lower triangular. This is very important. The transpose of an upper triangular matrix is a lower triangular matrix, and vice versa, which means the transpose of a lower triangular matrix is an upper triangular matrix. So if you have an upper triangular matrix, if you transpose it, you will get a lower triangular matrix, which is again very simple to prove. Because in an upper triangular matrix, aij is 0 if I is greater than j. Let's say this is the matrix A. This is an upper triangular matrix. Okay. Now if you take A transpose, in A transpose I will become j and j will become I, which means aij will become aji. Aji will become 0 if I is greater than j. Which means that if you swap them, you will get aij is 0 if I is less than j, which is a property of lower triangular matrix. So if A is upper triangular, A transpose will become lower triangular and vice versa. Again, you can take a very simple example to prove this. So let's take a upper triangular matrix 1, 2, 3 and 0. This is an upper triangular matrix. And if I take the transpose of it, I'll get a lower triangular matrix. Transpose will be 1, 0, 2, 3. So this is a lower triangular matrix. Okay. So the transpose of upper will be lower and transpose of lower will be an upper triangular matrix. So this was another property of triangular matrices. Okay. Next, let's look at partitioned matrix. So a partitioned matrix divides a matrix into blocks of submatrices. So it's actually not a very mathematical concept. It's a theoretical concept. Like it's a way in which we visualize matrices, and actually we will use it in linear algebra later as well. Like when we see Gaussian elimination and other important algorithms, there we will see this particular concept, and like how this particular concept is being used is you can actually divide a matrix into partitions. And you can name them. So let's say if I have a matrix 4 cross 4 and its elements are a11, a12, a13, a14 and then A21, A31, A41, A22, A32, A42, A23, A33, A43, and then A24, A34, A44. It's a 4 cross 4 matrix. Okay, there are 16 elements. Then I can write this matrix as like different matrices. The most common one will be like you can divide it into chunks, like you can divide it into sub matrices. Like this is a sub matrix. Okay, and this is another. So like let me do it this way. Let's do it this way. Okay, let me copy the same matrix and I'll show you multiple ways in which we can partition it. So what I want to say is, let's say this is the original matrix. Okay, okay, now this, like I will show you one way of partitioning it, and then we will, like I'll show you other way of partitioning it. So if I just copy this matrix twice, okay, so then what will happen? So one way of partitioning it will be this one. Okay, I am dividing it into 2 cross 2 sub matrices. This is the first one, then this is the second one, then this is the third one, and this is the fourth one. These are 4 2 cross 2 sub matrices. I can call this entire matrix M11, and I can call this entire matrix M12, and I can call this entire matrix M21, and I can call this entire sub matrix M22. So I can write this entire matrix M as a 2 cross 2 matrix like this: M11, M12, M21, M22, where all these matrices are 2 cross 2 matrices. It is just a representation, okay? You cannot say that matrix M is now 2 cross 2. No, matrix M is still 4 cross 4. It's just that you represented it as a 2 cross 2 matrix where all the elements were matrices themselves. Now why do we do that? That we will see later. Right now you won't see the application. Later we will see, like when we do Gaussian elimination, we will like do like or some other like Gauss-Jordan elimination. Like what will happen? We will try to like reduce it in a form like this, where we will have some elements and here we want I. So I will just directly write I here, which means that here we have anything matrix and here we have a, let's say 3 cross 3 I matrix. So you will already, like you will know that this is nothing but an identity matrix of size 3, which means I am not writing all the elements, I am just representing, which means it I 3 cross 3 actually means an identity matrix of size 3, right? So you don't need to write all these elements again and again. We can just directly write it like this. Or if there is a sub matrix here which is a 0 matrix of size 2 cross 2, we can write it like this. Here there is a 0 matrix of size 2 cross 2. So you don't need to write the entire matrix, you can write sub blocks like this. This is what we called partitioning a matrix. We are just partitioning it. So here we created 4 partition. We can also partition it this way. Let's say we have a single element here, and here we have a column matrix, here we have a row matrix, and here we have a 3 cross 3 matrix. So you can write this in this way as well, like M11, M12, M21, M22, but here M22 is a 3 cross 3 square matrix, M21 is a 3 cross 1 column matrix, M12 is a 1 cross 3 row matrix, and M11 is a 1 cross 1 singleton matrix. Okay, so we can partition it this way as well. Okay, so this is how you can do it. But generally we do partitioning when they are famous matrices. So let us say in this matrix, this is I 3 cross 3. It is an identity matrix. So I can just directly write I 3 cross 3 here. So you will, like, I don't need to write all elements, it's just a representation. Now what happens is here, even in this representation, you can perform addition, subtraction, multiplication. So what will happen? Let's say now let's say now we have a matrix which has sub matrices, which has 4 sub matrices: M11, M12, M21, M22. It has 4 sub matrices of size 2 cross 2, which means all of them are 2 cross 2 sub matrices, and the entire matrix is 4 cross 4 matrix. Now if you want to add it, let's say this is matrix A. If you want it to add it to another matrix B, and let's say this is it can also be written as M11 of matrix B. Let's say these are for matrix A and these are for matrix B. Again we are partitioning it in the exact same way, okay. Then you can write the matrix C or the addition again as M11A plus M11B, then M12A plus M12B, then M21A plus M21B, and then M22A plus M22B. You can write it like this. Here these are matrix additions. So you are adding this 2 cross 2 matrix with this 2 cross 2 matrix and you are writing it here as a 2 cross 2 matrix. And that's what we do, right? We just have to add element, like all the elements element by element. So same addition will work here as well. Because you can consider this as adding a 2 cross 2 matrix with another 2 cross 2 matrix and writing it here. But essentially you are doing element by element addition only. So you'll get the correct 4 cross 4 answer. I think you can like imagine it. Or you can take an example and do it. Okay. So this is what happens. You can do addition and even subtraction like this. If you can subtract these two matrices by partition, and we can even multiply them. So what we can do is, let me show you the result. So we can even multiply them by partition. So firstly, let me give you the theory. So a partition matrix divides a matrix into blocks or submatrices. So a matrix can be written like this. Here A11, A12, A21, A22 are submatrices of different order. They can be of different order, they can be of same order as well. Okay. Now we can actually, so addition and subtraction I already explained you. So they can be performed blockwise. In block, dimensions must be conformable, which means their dimensions must be same. Then only you can add them or subtract them. So we can add partitioned matrices or subtract them if the dimension or the order of the partitions is exactly same, otherwise you cannot. So here in this case, we assume that the dimensions were same. We assume that here also all the partitions are 2 cross 2. Then you can do it. Okay. And similar way you can perform multiplication as well if the dimensions are conformable. So let's say here in matrix A, all of them are 2 cross 2 matrices. So they are both 4 cross 4 matrices and these are 2 cross 2 matrices. Okay. So you can write the product of matrix A and matrix B as the product of matrix A11 into product into matrix B11 plus A12 into B21. So essentially we are just multiplying a 2 cross 2 matrix by 2 cross 2 matrix. It is just the result of multiplication of 2 cross 2 matrix by 2 cross 2 matrix. But here inside we have again matrix multiplication. So we can do it this way as well. Okay, so it is like you are essentially we are treating matrices as elements. While writing the formula, and then again we will perform matrix multiplication. So this is how you can do it. Again, if you want, you can take an example of this to prove this particular point. Okay, so to prove this one, let's take an example. Cool. So let's take two 4 cross 4 matrices. Okay. Let's say matrix A is 1 0 1 1 minus 1 0 1 2 1 0 0 1, then 0 1 minus 1 and 2. Let's say this is the matrix A, and the matrix B is I'm taking a smaller number so that the multiplication becomes easier. Okay, this is the matrix B, let's say. So if I perform matrix A into matrix B, what will happen? I'm just doing it like row and column wise, like the full multiplication. So I'll have 0 plus 0 plus 1 plus 0, which is 1. Then we will have minus 1 plus 0 plus 1 plus 2, which is 2. Then we will have 1 plus 0 minus 1 and then 0, so it will be 0. Then we will have 1 plus 0 plus 1 minus 1, which is 1. Okay, let's go to the second row. We will have minus 1, 0, then 0, then 1, then 0, which is 1. Then we will have 1 and then 0, 1, 1 and 1 is 2, and then 2 and 4 is 6. Then you will have minus 1, which is minus 2, and then we will have minus 1, 1, minus 1 plus 1, we'll have minus 1 plus 1, and then minus 2, which is minus 2 again. Okay, so you can verify the calculations yourselves as well once. Anyways, we will again calculate it using partition matrix, so we will anyway verify it. Then we will have 0 plus 0 plus 0 plus 0, which is 0. Then we will have minus 1 plus 0 plus 0 plus 2, which is 1. Then we will have 1 plus 0, which is 1. Then we will have 1 minus 1, which is 0. Okay, then we will have minus 1 here. Then we will have 2 minus 1, which is 1, plus 4, 5 here. Then we will have 1 plus 1, 2 here. And then we will have 1 minus 1, which is 0, and then minus 2 here. So this is the product of matrix A and matrix B. Now if we do it partition wise, like what will happen if we do it partition wise? So the idea is we can write matrix AB, the matrix AB as, so if I take this one as M11A and this is M12, or like let's make it easier, let's write this matrix, okay, this square matrix as A11, this is as A12, then this is A21, and this is A22. Then here we can write B11, B12, and then B21 and B22, and all of these are 2 cross 2 matrices. All of these are 2 cross 2 matrices. Then the matrix product AB can be written as, so you will have this matrix A11, so here you will have A11 B11 plus A12 B21. So let me just verify the first 2 cross 2 matrix. Okay, let us just verify the first 2 cross 2 matrix, the rest 3 you can do on your own. So the first 2 cross 2 matrix should be this matrix. So if I just calculate this, A11 B11 will be what? It will be 1 0 minus 1, sorry, 1 0 minus 1 0, this is A11. Then B11 is 0 minus 1 0 2, then plus A12 is what? 1 1 1 2, and times B21 is this matrix 1 1 0 2. So if we calculate these 2 matrices, firstly let's calculate the product of the first 2 matrices. We will get 1 and 0. So here we will have 0, then here we will have minus 1, then we have minus 1 0. So here we will have 1, sorry, here we will have 0, here we will have 1. Okay, now we have to add the other product. So if we calculate the product of these 2 matrices, so we will get 1 1, so 1 and then 3. Then we have 1 2, so we will get 1 and 4 plus 1 5. So this is the product of these 2 matrices. Now if we add these 2, we will get the matrix 0 plus 1 is 1, then minus 1 plus 3 is 2, then 0 plus 1 is 1, and 5 plus 1 is 6. We got the matrix 1 2 1 6, which is the same as this matrix 1 2 1 6, right? So this is how you can do it. Now you can compute the rest 3 values as well, like again, like we just considered these matrix partitions as elements and we can perform it this way. Okay, so this is how partitioned matrices work. We can add them, subtract them, multiply them, and we can actually consider the partitions themselves as elements and perform the operations. The only thing that you need to remember is the conformability, which means if we are adding or subtracting and multiplying, the order should be as such that that particular operation is possible, then only you have to perform it. Okay, cool. So this is all about partition matrices. Okay, now let's look at the next concept, trace of a matrix. So how is the trace of a matrix defined? So it's very simple. The trace of a matrix refers to the sum of the diagonal elements in a square matrix. So it is only defined in a square matrix, and in the square matrix the trace of a matrix is the sum of all the diagonal elements. We already know what diagonal elements are. the elements on the diagonal or the primary diagonal are the elements for which the row number and column number are equal, which means I will be equal to j, okay, and that is the primary diagonal, and sum of all those elements is called the trace of the matrix. So trace of any matrix A is nothing but the sum of all the elements I, where I is going from 1 to n, which means A11 plus A22 plus A33 plus A44 and so on up till ANN. So for any square matrix A where the ijth element is Aij and it is of size n cross n, the trace is the sum of all diagonal elements. Very simple. So if you want an example, we can take a very simple example here. If the matrix A is, let's say, 3, minus 2, 7, 15, 2, 8, minus 9, 7 and then 6. Then the trace of this matrix is the sum of diagonal elements, which means 3 plus 2 plus 6. It will be 3 plus 2 plus 6, which is 11. Okay, this is how we calculate the trace. And these elements can be negative as well, and in that case you will add the negative number. Okay, so this is how we calculate the trace of a matrix. You just have to add the diagonal elements, that's all. Now there are certain properties of trace of a matrix. So trace of the matrix A plus B will be equal to trace of A plus trace of B. Very simple, because in matrix A, so what will happen? The trace of matrix A will be what? It will be summation of all the diagonal elements of matrix A, and the trace of matrix B will be what? It will be sum of all the diagonal elements of matrix B, BII, and we know that for both of these to be addable, both of them must have the same size. If A is n cross n, B also must be n cross n. Okay, then only trace is defined. It has to be square and they have to be of the same size. And hence the trace of the matrix A plus B will be what? In A plus B, we will again sum all the diagonal elements and they have to be added element by element. So it is just nothing but summation of I equal to 1 to n AII plus BII, because the IIth element will be the sum of corresponding elements. So we will have AII plus BII, which is nothing but you can take it as you can take the summation inside and you will get AII ka sum plus summation I equal to 1 to n BII sum, which is nothing but trace of matrix A plus trace of matrix B. Okay, so it is a very simple mathematical proof. Here we have proved that we have proved the first theorem. Now second is, if you are multiplying a matrix by a scalar, then the trace also gets multiplied by the same scalar, and this is also very simple to prove. So trace of matrix C times A will be what? It is summation I is equal to 1 to n, and the element in the diagonal will become C times AII. It will become C times AII, and you can take C out because C is just a constant. It is a scalar constant, and this will just become C times the trace of matrix A. Okay. For all of these, you can take examples as well to verify it. It's very simple. Okay, you can take an example as a homework. You can do it on your own. Okay. The next property is trace of matrix AB will be equal to the trace of matrix BA. So for AB and BA, the trace will be equal. This is an interesting property. Let us try to prove it. So the property that we just saw is trace of matrix AB is equal to the trace of matrix BA, which means the sum of diagonal elements in AB and BA will always be same. Okay. Why is it so? Because actually, okay, let's see. So in AB, the diagonal elements will be what? So if let's say A is of size n cross n and B also must be of size n cross n, then only the multiplication will be possible. So in AB, let's say the product AB is defined as C. Then let's say the ijth element in A is Aij and jkth element in B is Bjk. Then we know that Cik. Actually, we are only worried about Cii, which means we are only worried about the ith row and the ith column of C, right? Because we want the sum of all of them to calculate the trace. So Cii will look like summation j is equal to 1 to n Aij times Bji. right? This is the ith element of C, where the row and column number are equal. Now if you look at BA, so let's say in BA the ijth element looks like Bij, and in A it looks like again Ji, and if this is D, then in D also, like the ith element will look like summation j is equal to 1 to n, because the cardinality is same or the order is same. You will have Bij times Aji, right? Okay, so here it might look like that the ith element in C is not equal to the ith element in D. The elements might be different, because here we have Aij and here we have Aji, so the elements are different. These sum are not equal. For any ith element, we are not saying that the every diagonal element will be equal in both of them, but their sum will be equal. We are saying that the trace of AB will be equal to the trace of BA. So based on this, what can I say? The trace of the matrix C, which means trace of the matrix AB, will be what? It is the sum of all diagonal elements. So this is the ith diagonal element, or ith row and ith column. So the trace will be, you will have to sum over all I as well. So it will be summation I equal to 1 to n. Then at ith row and ith column, the element set which is sitting is this one. So it will be summation j is equal to 1 to n Aij times Bji, right? And similarly, the trace of matrix D will be what? Trace of matrix D will again be summation I is equal to 1 to n, summation j is equal to 1 to n Bij times Aji. Now if you look at both of these two are equal. These two are equal because I and j both are going from 1 to n. I and j both are going from 1 to n. Basically you are taking all possible pairs of I and j. Okay, so it is like when I and j are 1, you will have A11 into B11. Here also you will have A11 into B11. And when I is equal to 1 and j is equal to 2, here you will have A12 into B21. Here also you will have A12 into B21 when j is equal to 2 and I is equal to 1. So you will have exactly same elements here and here. You can come like expand it and see, right? And hence these two values are exactly same. Trace of C is equal to trace of D. So trace of matrix AB is equal to the trace of matrix BA. Okay, this is how we can prove it. Again, diagonal elements can be different, but their sum will be same. We can take an example again to verify this thing. So let's say that the matrix A is 2, 3, minus 1 and 4, and the matrix B is 1, 1, 7 and 2. Then the matrix AB will be what? The matrix AB will be 2, minus 1, 3 and 4 multiplied by 1, 1, 7 and 2. Both are 2 cross 2 matrices. So the product will also be 2 cross 2 matrix. So it will be 2 minus 7, which is minus 5. Then you will have 2 minus 2, which is 0. Then you will have 3 plus 28, which is 31. And we will have 3 plus 8, which is 11. Okay, and if we compute the matrix BA, we will have 1, 1, 7, 2 multiplied with the matrix 2, minus 1, 3 and 4. So if we compute this matrix, we will have 2 plus 3, 5. Then we will have minus 1 plus 4, 3. Then we will have 14 plus 6, which is 20. Then we will have minus 7 plus 8, which is 1. So this is the matrix AB and this is the matrix BA. You can see that the diagonal elements are different. Here we have minus 5 and 11. Here we have 5 and 1. The diagonal elements are different. But surprisingly enough, trace of the matrix AB is what? Trace is minus 5 plus 11, which is 6. And also the trace of matrix BA is what? It is again 5 plus 1, which is 6. And the trace is equal. The trace of matrix AB and the trace of matrix BA will be equal. We proved it mathematically. And we saw an example as well. Okay, cool. So this was another property of trace, and the last one is trace of matrix A transpose will be equal to the trace of matrix A, because the diagonal elements in A transpose and A are same. We already know this because I and I are same. In transpose I becomes J and J becomes I, but anyways we are summing up diagonal elements. In the matrix A and its transpose, the diagonal elements remain same if A is a square matrix, and hence the trace will be same in the A transpose and the matrix A both. Okay, so these are a few properties of trace of a matrix. Cool. let's move ahead. Okay, now let's see a few examples. So this is the first one. If A is an involutory matrix, then which of the following statements is or are true? So A is given to be an involutory matrix, which means A square will be equal to I, right? And A is a square matrix. The first option is A and A to the power 98 are equal. So what is A to the power 98? It is A square into A square. You can write it like this: A square 49 times. 49 times, right? Because if you write 49 times, it will just become A square to the power 49, which is A to the power 98. Now all these A squares are just I. They are just I into I into I 49 times. Now I into I is I, we know that, and you multiply identity matrix any number of times by itself, you will just get the identity matrix. And hence A to the power 98 will also be equal to I. It is not equal to A, it will be equal to I. So the option A is A to the power 98 will be equal to A. We cannot say that. We don't know what matrix A is. We just know that A square is I. And hence option A is incorrect. But option B is correct. A to the power 98 will be equal to I. So option B is correct. Now let's look at option C. In option C we have A square plus A to the power 4 and so on plus A to the power 2n. What will this be? So how many terms we have here? 1, 2. So we will have 2n by 2, which is n terms. We will totally have n terms. So A square is I and A to the power 4 will also be I and so on. A to the power 2n will also be I by the same logic. They are all I. Okay, if you have an even power, they will all be equal to I. And it is n times. It is also n times. And hence this sum will be equal to n into I. N times you will have I. Right? I plus I plus I. I plus I is not I. I plus I is actually 2I, right? Because if you have an identity matrix, if you add it with itself, you will not get another identity matrix. You will get 2, 2, 0, 0, which is essentially 2I, right? So if you add identity matrix n times, you will get ni. So this sum is n times I, but in the option we are given 2 times ni. 2ni is not equal to ni, and hence option C is incorrect. None of the above is not correct. Option B is the one which is correct. Only option B is correct in this question. Cool. Let's move to the next question. Here only option B is correct. In the next question we have lots of true and false. Let's look at them one by one. First is, if A is idempotent, 2A minus I is involutory. So let's solve them. So in the first question they are saying, if A is idempotent, we just have to, we don't have to prove, we have to say that it is true or false. So if A is idempotent, we have to find is 2A minus I, what do we have to check? Involutory. Okay, is it involutory or not? Does this mean that this will be involutory? So how do we check this? A is idempotent, it means that A square will be equal to A, right? And A will be a square matrix. Now we need to check that 2A minus I is involutory or not. For that we will just take the square of it. 2A minus I square will be what? It will be 2A minus I times 2A minus I. So we can expand the bracket and we will get 2 into A minus 2 into A into I. Always write, whenever you are multiplying matrices, you will have 2A into I. So the order matters. And minus we will have I into 2A, which is 2 into I into A. Scalar multiplication, you can do it in any order. We have seen this property. Then we will have plus I into I. Okay, this is what the expansion will be. Now 2 into A, which is 2A square. Now A square is equal to A. So I can just write it equal to 2A. And A into I, if you multiply any matrix by identity matrix, you will get the same matrix back. It doesn't matter where you are multiplying the identity matrix. So you will get minus 2A, and this will also be equal to minus 2A. Oh sorry, here it is 2 times 2, so here it is 4. I made a mistake. This is 4 times A into A. So this is also 4 times A. Okay. This is 4 times A square, so 4A. Okay. So minus 2A, and here we have plus I into I, which is I. Okay, So now we will have 4a minus 2a will cancel, because 4a minus 4a is just the zero matrix. You should not cancel it like that, because these are matrices actually, but with practice you will understand. So you can write 4a minus 2a as the zero matrix. It is the zero matrix, and zero matrix plus identity matrix is just the identity matrix. So at the end you got an identity matrix, and we just figured out that 2a minus I whole square is the identity matrix. It means that 2a minus I is involutory, because for any matrix, if a square is equal to I, then that matrix is involutory. So if a is idempotent, then 2a minus I is involutory. We just proved that, and hence first option is true. Okay, now let's look at the second one. If a is involutory, a plus I plus a, I minus a is 0. So second one is saying if a is involutory, then I plus a, I minus a is 0, I guess. Yes, this is what we have to check. Okay, so if a is involutory, a square will be equal to I, and this product will be what? I into I minus I into a plus a into I minus a into a. So this product is what? This is what we have to check. So this product I expanded. I into I is I only, I into a is a only, a into I is a only, and minus a square. A square is I. So I can write I here. Now I minus I is the zero matrix, and here we have, sorry, this is plus. So and minus a plus a is also the zero matrix. So it is zero matrix plus zero matrix, which is the zero matrix. And hence if we expand this bracket, if we expand I plus a, I minus a, we indeed got the zero matrix, which is correct. We wanted zero matrix only. So yes, I plus a, I minus a is the zero matrix. Here 0 is the zero matrix, we are assuming that. Then this statement also becomes true. Okay. Now next is the matrices I plus a by 2 and I minus a by 2 are idempotent if a is involutory. So the third one is saying if a is involutory, then I plus a by 2 and I minus a by 2 are idempotent. We have to check this. Okay, so let's check. If a is involutory, then a square will be equal to I, and we have to check about I plus a by 2 and I minus a by 2. So if I take I plus a by 2 square, I plus a by 2 is a matrix, and if I take the square of it, half is a scalar. It is just like, you can write it like this, half into I plus a whole square. So it will just become 1 by 4 times I plus a times I plus a, where I plus a and I plus a are matrices. So you can write this one as 1 by 4 times I into I plus I into a plus a into I plus a into a. Now a into a is a square, and a square is equal to I because a is given as involutory. So we can write this entire thing as 1 by 4 times I into I is the matrix I is the identity matrix, I into a is a, and a into I is a, and a into a is I. So we got 2i plus 2a, we got 2i plus 2a, which means 2 times I plus a, so we can take 2 out and we will get 2 by 4 times I plus a, which is I plus a by 2. So if we take I plus a by 2 as a matrix Q, then we just proved that Q square is equal to Q. It means that I plus a by 2 is idempotent. It is idempotent. Now we can do the same thing for I minus a by 2 as well. If I do the same thing for I minus a by 2, its square will be 1 by 4 times I minus a times I minus a, which is I into I minus a whole square, which is I into I minus I into a minus a into I Okay, I minus a whole square, which means I minus a into I minus a. So we have I into I minus a minus a into I plus a into a. This is the matrix that we have. So this is I into I is I, this is a, this is a. So it will become 1 by 4 times this and this are I. So 2i minus 2a, which is nothing but I minus a by 2. So for I minus a by 2 also we just proved that I minus a by 2 square is nothing but I minus a by 2, which means I minus a by 2 is also idempotent, and hence both of them are idempotent. So if matrix A is involutory, I plus a by 2 and I minus a by 2 both are idempotent. This is how you solve questions in exam. If any type of matrices are given, you just need to take a square of them. Just remember the property and try to prove it, and mathematically you can do that. Okay. So third one is also correct. This is also true. Okay, now next is if A is idempotent, then A transpose is idempotent. Then we have if A is involutory, then A transpose is involutory. If A is nilpotent, then A transpose is also nilpotent. So we just have to prove the properties for transpose. So if A is idempotent or involutory or nilpotent, what will happen to the transpose of it? So let's try to see that. So if firstly let's try to do it for anyone. If involutory, let's say if A is involutory, it means that A square is equal to if A is involutory, A square is equal to I, which means the square of A is the identity matrix. So what will happen to the transpose? A transpose square will be A transpose into A transpose. Right, A transpose square will be A transpose into A transpose. Now if A square is the identity matrix, can we say that A transpose into A transpose will also be the identity matrix? We'll have to think about that. So what happens here is, so there is a very interesting property of squares and transposes. So what happens is A square transpose is equal to A transpose square. For any square matrix A, this property holds true. A square transpose is equal to A transpose squared. The reason is A transpose square is what? It is A transpose into A transpose. And we know that AB transpose is B transpose A transpose. It means that if I do A into A transpose, it will just expand in the reverse order, which means it will just become A transpose into A transpose, which is nothing but A transpose square, and this thing is nothing but A square, A square transpose, and hence A square transpose is equal to A transpose square because of this property. Okay, and hence if A square is I, then A square transpose will be what? A square transpose will be what? It is I transpose, and transpose of an identity matrix is the identity matrix itself, and A square transpose is equal to A transpose square, and hence A transpose square will also be equal to I, which means that A transpose is also involutory. It means that A transpose is also involutory. Now based on the same property, based on this exact same property, we can prove the remaining two as well. Right, based on the exact same property, because A square transpose will be equal to A transpose square. Based on the exact same property, take it as a homework. You can prove the same thing for idempotent and nilpotent as well. Try to prove it on your own. Idempotent and nilpotent as well. Just remember this property will hold. Okay, based on this you can prove both of them. So if A is involutory, its transpose will be involutory. If A is idempotent, its transpose will be idempotent, and if A is nilpotent, then its transpose will also be nilpotent. Okay, so all these three conditions will hold true. True, true, true. Okay, and the last two I am giving you as homework. You can try it on your own. Cool. Now let's move to the next example. Okay, so a matrix is given. Matrix A is 1 2 3 0 1 4 0 0 1, and you are given a matrix B which is A transpose into A. So you have to find the value of trace of B. Okay, so let's try to compute A transpose into A. So what is the matrix A transpose here? We just have to take the transpose, so it will become 1 0 0 2 1 0 and 3 4 1. This is A transpose, and the matrix A is 1 2 3, then 0 1 4, then 0 0 1. So, and we have to calculate the trace of this. This is the matrix B. We have to calculate the trace of this. We don't have to calculate the entire product. We just have to calculate the diagonal elements, but let's calculate the entire product. Okay, there is no harm. So what is the first element? It will be 1 because we have 0 0, so these two values will become 0. We will just get 1 2 3 here. Then we have 2 1, so we'll have 2 here, then 4 plus 1 5 here, and then 6 plus 4 10 here. Then we have 3 4 1, so 3 here. Then we have 3 2s are 6 plus 4 10 here, and then we will have 9 plus 16 plus 1, which is 26 here. Okay, so this is the matrix A transpose A. This is the matrix A transpose A. And now if you calculate the trace of B, here we just have to apply the formula. Okay, we just have to do the multiplication and calculate the trace. So trace of B is the sum of diagonal elements. So it is 1 plus 5 plus 26. 1 plus 5 plus 26, which is 6 plus 26, which is 32. So the trace of the matrix B is 32. Okay, this is how we can calculate it. Just remember the multiplication logic and we can do it. Here we have calculated a transpose, then multiplication, and then we have calculated the trace. So the answer is 32. Okay, cool. So these were a few questions on spatial matrices, which means different types of matrices. And with this, matrix algebra comes to an end. So yeah, thanks for watching the lecture. Let's meet in the next lecture. Bye bye.